continue with Daniel Sheinbaum, who studied mathematics, did a master in physics, did a PhD in mathematics at UBC in Canada, and then I did a postdoc in physics at the same Stab in Mexico City, and now he's at CICESE, which stands for
Centro de Investigación Científica y Educación Superior de Ensenada.
Exactly. So Daniel, thank you for coming.
Okay, no, so thanks to everybody for being here.
This question.
Yeah.
So what's the last E?
The last E, Ensenada,
The place,
city.
the city.
Ensenada is
Okay.
close to Tijuana.
Beautiful place.
So superior in
Ensenada. So
Thank you.
say it in English and then international.
No, it's,
I don't know, it would take me a long time.
Okay.
Yeah. So this talk will be, I think, very different in style from most of the talks you've seen. It will be, I guess, a bit more similar to Bernardo's talk. So I hope you enjoy it. So this is based mostly on joint work with Omar Antolin, who's at UNAM in the Institute of Mathematics. This by now it's a bit of old work, but it hasn't been picked up, so I'm sure it's going to be new for most of you. And well, it's more in line with the conference. Okay. So this is the outline, and so first I'm gonna give some background and some of the assumptions behind what people do to classify what are known as SPT phases. Then I'm gonna present formalism that Omar and I did that I called like a generalized Brillouin zone, and then you can use equivariant cohomology to say something about interacting crystalline phases. And so I will then compare to what is done for crystalline SPT phases. What the most popular classification is by Brian Thongren and Dominic Van Els. I think somebody here works with Brian. Yeah. Okay. So please let him know what I say here and see if he's interested. Okay. And in the last part, I will briefly discuss generalizations in the hopes that well, some people here, like topologists or people who know about von Neumann algebras, or even people who do theory but do more like numerical stuff and things like that, can help me out to sort of continue this line of research. Okay. So we've seen a lot of non-interacting invariants or systems, and I'm not going to talk about those, but later they will pop up. However, well, never mind. So let me continue here. Okay, so SPT phases are phases of systems that have interactions, right? But they're supposed to satisfy some properties. So they're supposed to have a unique gap ground state, right? They have to commute with an internal symmetry group, and they're supposed to be, their ground states are supposed to be trivial if you do not respect the symmetry. Okay, so that's why so SPT means symmetry protected topological phases, and that's supposed to mean that if you break the symmetry, you lose your invariant. Okay, and they're supposed to be additive and they're stacking. Okay, which is something that is usual, right? The group structure that appears when people use things like K-theory for non-interacting systems. K-theory gives you a group, and the notion of adding two elements of your group is supposed to correspond to overlapping two systems and getting a new system that is sort of like the result of the group operation. And finally, there's like this is not well defined mathematically, but there's like a rather physical notion, which I think is tantamount to saying that there's no anyons in your system, but generally they just say, oh, there's no long range order and or no topological order as well. Yeah, I think that in general. Okay. So this is supposed to be an example. So this in one dimension. This is a spin chain, and so this is a spin one for each point on your lattice. However, your ground state can be sort of like rearranged and decomposed. These are these entangled single pair. And the point is that there's this dangling mode at the edge of your system. And so this is a projective representation of your group G. G acts on each side, okay? So, and projective representations turn out to be classified by what is known as the second group cohomology. So I know most of you are not familiar with group cohomology. I'm not gonna familiarize you much more, but so yes.
How is G acting on the point? What do you mean by
So-
the symmetry
so-
of the point?
So G has, so here on each point you have a vector space, right? That vector space is a representation of your group, okay? But on your
So I don't think that I have a symmetry of the system on which.
I mean, it is because you have an operator that acts on each side, right?
Okay.
Okay, but then, so then the point is that this symmetry at the edge becomes projective. Okay, there's a face, and yeah, like I said, those are classified by this group cohomology. Okay, let me go quickly because so the first part is I'm not gonna give you a lot of details. Sorry about that, but if you do have questions, do stop me. I'll try to say more. So okay, so that's more or less well understood in one dimension, but how at higher dimensions, right? And so these people who were at the time at Perimeter, particularly Xiaogang Wen is a very famous professor at MIT. So they suggested this classification for bosonic D+1 GSPT phases, and they proposed that you just instead of so here if we go back, you notice that here I can write 2 as 1 plus 1. And so they said, okay, keep the plus 1, but instead of 1, right, put the dimension, right? Our dimension was p equals to 1. Here, this is what. So this is what they do. And so, okay. So here, if group cohomology seems complicated, this is ordinary cohomology. It's what's known as Borel cohomology. Okay, of this space here that I'm not going to explain to you, which is called the classifying space. So generally, the classifying space of a group, well, it depends. For discrete finite groups, you usually get infinite dimensional spaces. So here you're computing like ordinary things you've seen, but instead of toruses and things like that, whenever you have symmetry, usually this space or something similar to that crops up, and these things can be quite complicated. And it turns out, so also you've probably normally seen only cohomology with integer coefficients. So there's a U1. And so I'm passing here to, so it's not hard to show that you just add a degree here and instead you use C coefficients, which is the normal cohomology you're used to. And this D plus 2 will be very important later on. So keep in mind that number, exactly, D plus 2. Okay. So are these all possible phases? What about fermions? And so people said, okay, this classification kind of works well for bosons, but we should generalize it to include fermions. And so these people who are also very famous, particularly, well, Anton Kapustin is very famous, but these two are mathematicians and are algebraic topologists that are also pretty famous. They came up with an approach that says, okay, let's go beyond group cohomology, and SPT phases will be classified by this thing here. Okay, so let's read this carefully. Relativistic, weak-rotated, invertible, extended topological quantum field fields.
Exactly.
Okay. So, and I emphasize particularly these two things, okay, which I will discuss a bit at length. Okay, so what does relativistic plus weak-rotated mean? Okay, so we have to be careful here, but in the formalism of Fried and Hopkins, they use a symmetry group, right? This G was the internal symmetry group, and they sort of extended the symmetry group to include this group here. And notice the D plus 1. So this is a weak rotated version, which what it means is a Euclidean version of Lorentz transformations. Okay, so for them, Lorentz transformations are very important. They're actually fundamental in their classification. Your system somehow has to have emerging Lorentz transformations. Okay, and a TQFT is something that's hard to explain in one slide, but I'll try my best. So the idea is you first have to start with bordism. So imagine you have two circles, okay, and you can join them into one circle this way. This is the most famous bordism. It's called the pair of pants. And so this is in D equals 1, right? And what our TQFT does is it assigns to the boundary of this whole thing, it assigns vector spaces, and to the whole thing, it assigns a linear map between them. Okay? Are there any questions? I'm here being very, I'm not giving any details. Okay, so, yeah?
Is this the appearance of OD plus 1 related to saying like you want your TQ to be oriented or something?
There are, yes, there are spin bordisms and things like that. Okay. So invertible here means that B1 and B2 are one-dimensional. So that might seem like a very trivial thing to do, but it turns out it isn't. It's actually quite complicated, and classifying these things was a theorem that was proved relatively recently. I think to the full extent, it was only proved a year ago. So this is very modern mathematics, okay? And the extended part, I don't have time to explain here. Sorry for rushing a bit. But it implies that you use higher category theory, and there's a very beautiful theory that has been developed, particularly by Jacob Luring, but I will not get into that. Okay, so did Chen, Gu, and Wen, did their proposal have an emergent spacetime, right? Did you need Lorentzian symmetry to appear? And it turns out that they sort of don't discuss it very much, but they do, right? So you can find it, here's where you can find the citation. And yeah, this thing here actually classifies what are known as topological gauge theories, and it's a subset of topological quantum field theories. And they use these things. Okay, so this is my warning. So I have to clarify that this is not, so what I'm gonna say next is not the perspective of most of the community. Okay, I do have to be very clear about that. At least not most of the SPT community, who are more optimistic. However, right? So what bothered me a lot was, okay, as a topologist, I love the fact that TQFT appears, and that's all very wonderful. But as a physicist, I jump at the fact that you need Lorentzian symmetry, right? And this is very important because, okay, someone might say, okay, well, in non-interactive systems, we have Dirac cones, we have things that look locally like something relativistic. But for the classification, right, for the K-theory classification, for doing a lot of stuff, the relativity doesn't get anywhere in it. Okay, you don't need it at all. And so one could ask, okay, why would I need my system to have Lorentzian symmetry? Particularly, it seems something that's very easy to break. Suppose I can construct some system that does have this emergent symmetry. Can't I just wiggle things a little bit and suddenly I break it? Okay. So I went and I said, okay, but these people are very smart, and maybe I'm just not understanding something. So I went to talk to them. Particularly, I went to talk to
Einstein.
Yes, deeply in my thoughts. I said, Einstein, what should I do? No, I went to talk to
space-time.
I went to talk to Dan Fried and asked him, well, why do you assume this relativistic symmetry? And he said, yeah, we don't know. We have no idea. We think it works, right? And for our theorem and for the stuff that we do, it seems to work well, and it seems to agree with what other people are doing, particularly in high energy. But the answer is we don't know, right? Okay. So I think that they are in general more optimistic that this problem will be sort of solved, that they will be able to explain why you have a Lorentzian symmetry emerging. But it's something that I want to stress that I'm not the only one worried about. So at first I thought I was a bit, like nobody really cares so much about this, so maybe I'm not understanding what's going on. But then I saw this talk, which I highly recommend, by Davide Gaiotto, and when he discusses the difference between gap phases of matter and topological field theories, and he does say, well, there is some relationship which is rather remarkable that seems to work. No, I think he's a bit more optimistic than me. However, he does say, well, why things like the fermion structure, the pin structure, or the spin structure of a manifold should be relevant for this classification. Okay, and he says in this talk, I mean, he says many things, but one of them he says is, well, these things might start to diverge, right? These things might not be equal to this. And when I really want to emphasize a point here that I think it's not often discussed, which is, so I want to engage the audience. So what topological phase is this system in? Can anybody tell me? No?
Great.
Huh? No? Okay, so this was supposed to be the obvious example, and the answer was supposed to be, oh, well, this is like a quantum spin Hall effect, right? And these edge states are protected by time reversal symmetry. Okay, so if you go and compute the invariant, I think you can do it with the Fourier curvature. You'll get a non-trivial C2 invariant, right? A mod, something like pi mod 2 pi. But that answer would be wrong, right? Because I haven't told you that you're gonna respect the symmetry. What if I break the symmetry? Then this system becomes trivial, okay? So going ahead and computing some invariant doesn't really tell you what phase your system is in, right? You have to first figure out the possible phases, the possible restrictions. Okay, so the question then is, what are we missing out if we impose Lorentzian symmetry? Are there some phases that we are missing because we expect, so we don't count them because they don't have Lorentzian symmetry? Or the other way around, are there systems that could be connected to the trivial phase because if we break Lorentzian symmetry, you don't get it. You don't have this trivial invariant anymore. And here, I'd like to mention the work of Garat, who's a fantastic mathematician. And she had sort of positive results, and so positive in the sense that she proved that for d equals 2, you do get what you would expect from the Chen-Wu Wen classification. Well, not exactly. So what you get is that this is an invariant. There might be more, okay? But at least you do get this. And she proved it without using relativity, okay? Without using emerging topological gauge theories.
What kind of books are you looking at?
So she's looking at, I think generally, these finite, I think she's looking at compact Lie groups in general for this G. But maybe
I
I'm
thought
not.
it was finite.
Is it finite?
I'll check.
Okay, sorry. Yes. So it might be finite. Okay. So on the other hand, she has a very recent paper where she has an SPT phase that does not respect CPT, and hence it doesn't satisfy the relativity, right? Because CPT is a theorem when you impose Lorentzian symmetry. I think even if you impose the weak rotated version. So yeah. So there are things that I want to miss. And finally,
Sorry. So CPT is a theorem about Lorentz invariant local QT. Well, I mean, if it's like if there are no local terms, it already doesn't work. Like low energy effective field theory, if I'm not mistaken. But it's a very specific theorem about 4-dimensional, 3 plus 1-dimensional Lorentz invariant local QT.
yes, but I don't see why it's in contradiction with this. So what you're saying is that the topological field theories don't have local degrees of freedom or something like that?
No. The terms of Lagrangian. It's like the terms of Lagrangian must be local, which is not even the case in the law. Effective field theory. Like you can write that. Crazy field.
Well, to my understanding, you do need to assume Lorentz symmetry, for example, for all the classifications. So I'm sorry, I'm just maybe not understanding your point. Well, so how is it related to what I'm saying?
Well, how is what you're saying is contradicting anything?
Okay, so what I'm saying is that so you're saying okay, you shouldn't have CPT if you have
Yeah, Lorentz invariance doesn't imply CPT. You need locality of like I mean it's a very specific theorem in
well okay maybe
local,
maybe we can discuss it more later, but I'm pretty sure that, for example, all these classifications have CPT in them in general.
Yeah.
Okay, so yeah, so maybe the causal link is not that clear, but I'm pretty sure that you have
part of the
CPT in them.
reflection positivity.
Yeah, I mean reflection positivity is weak rotated
Yes.
version of unitarity, no?
Yes.
So but yeah. Okay. And finally, okay, so something I also want to stress for people that are not in the field is that there are several proposals, right? There's no general consensus yet. They're more or less agreeing in some cases, but there are several different proposals for classifying SPT phases, okay, with different predictions. So I think this work is known, but maybe not that well known by Xiong, and he does so he tries to come up with some predictions that could be true for all possible classifications. Okay, but so there's no agreement. There's different possibilities, and many of them, most of them, as far as I understand, do assume this emerging Lorentzian symmetry. Okay, so almost all of the proposals fall under Kitaev's conjecture. Okay, and Kitaev did not assume Lorentzian symmetry, but he did say, okay, SPT phases form a spectrum. Okay, so what is a spectrum? Well, a spectrum in the sense of algebraic topology, and I'm again not gonna have much time to explain what that is, but so suppose your set of ground states for d-dimensional SPT phases forms a space, right? Consider the set, and you give it a topology. And a spectrum means that there's a map from this thing here to this thing here. So this is the d plus one-dimensional space. This thing here is called a loop space. So you take base loops. I think the base point is supposed to be the trivial state. And there's supposed to be a map to these things. And I think in general, they're assuming that there's actually a homotopy equivalence between the two things. Okay, so almost all of them assume something like this, right? That SPT phases form a spectrum. And what is the upshot of doing that? Well, the upshot is that I can compute the set of phases, right? If I want to look at the different phases and I move some parameter, this would be like the components of my space. Well, that's equivalent to computing this generalized cohomology theory. Okay, and these things are, this is easy to define, but hard to compute. This is much harder to define in some sense, but it's much easier to compute once you have the techniques. And okay, some issues that I see. I mean, these are not as big issues, but okay, I'm gonna mention them. So the first is that this is a bit counterintuitive, right? There are some proofs, like I mentioned, but this is a bit counterintuitive because you have sort of like a d plus one dimensional system. You look at families of these d plus one dimensional systems that sort of come back to your original one, and somehow you end up with a system in a lower dimension, right? So this dimensionally is kind of counterintuitive. Doesn't mean it's wrong, but you have to be careful with that. Okay. The second thing is that until we know exactly what this thing is, this proof that these two things are the same will always be a bit hand wavy, right? Because proving topological equivalence between two spaces, you need to know what the spaces are in general, right? I mean, sometimes you can say some properties that will allow you to put them in the same type as, the same homotopy type or whatever, but in general, this is very hard. Third, and this is something that made me reject the idea for a long time, but as we will see later, you can sort of resolve it in a very interesting way, is that this looks, again, to be false for non-interacting systems, right? So for free fermion phases, usually you have a KR group, and for the Brillouin zone, and the dimension appears right in the space and not in the degree. Okay, so that would seem to be like, okay, what's going on here? Because over here the dimension appeared in the degree of your group. Okay. Okay, but we will see how this is resolved. Are there any questions?
Is the hand wavy proof you're talking about, is that like Theo, Johnson, Fry, WTO, those proof?
No, I mean that's one proof that they use something like defects. I think that's the one that I understand more. There are other ones. For example, Xiong has one where they use like a towelless pump picture of it, and they go back and sort of like they do some computations, and I don't think they're wrong, but I think it hasn't been embraced by the mathematical community because it's hard to translate a bit. I'm not saying they're necessarily wrong, but I'm just saying these things are kind of a bit counterintuitive. Okay. And finally, crystalline SPT phases. So all of the things I said before was for an internal symmetry group G. What about spatial crystalline symmetries, right? So what we do in non-interacting systems is usually for discrete translation symmetry, and you can add some rotations and reflections. And so here comes the work of Ryan Thorngren and Dominic Else, who I think they had a very, very interesting idea. They call it the crystalline equivalence principle, which I mean, summarizing their work, which was, I mean, they put a lot of things into it. It boils down to saying, okay, just replace G by the crystalline group, right? Use the same formula, but just replace, instead of having an internal symmetry group, just use your crystalline group, and it still works out. Okay, good. So, are there any questions? Okay, thanks. So I've been ranting for a while now, and instead of continuing to rant, I would say, okay, can I say anything about trying to classify interacting systems, right? And then you can criticize whatever I propose here. Okay, so by putting some restrictions. So let's go back to the single particle case. And so this is the traditional way that people see Bloch's theorem, right? So you have a periodic potential, and then your eigenfunctions are essentially eigenfunctions of the translation operator multiplied by a phase, right? That's how we normally see it in textbooks. However, there's a much more mathematical way of putting it, and this will be useful for us. So if this is your single particle Hilbert space, right? Just square integral functions on RD, and B represents spin. It won't be very relevant for the discussion here. Then H is a representation, okay, of your group of set to the D. And as such, it can be decomposed over its characters. Okay, this is called I believe it's called the isotypic decomposition. So, and the characters for set to the D are precisely the points in the Brillouin zone, right? So the characters are things that are, well, they're functions that go from your group to U1, and they respect the group law. And so here we always get, right, e to the k dot a. This lives in U1, so k is really representing a character. This is well known. Okay. And so you can decompose your Hilbert space, and probably many of you have never seen this thing here. Huh? Yeah. Okay. So this is a direct integral, exactly. Is that what is known as a direct integral decomposition, right? So you sort of separate your Hilbert space into sectors, one for each point on your Brillouin zone, right? The problem is, right, this is the analog of what a direct sum would be. The problem here is that you have an infinite, a continuum of points, right? So when you have a continuum, you have to replace the sum by something that has a measure in it, and this is called a direct integral. But the point is that this Brillouin zone, right, pops up by using representation theory, and I never use the Hamiltonian here. So this is quite important because people often think that you need to use the Hamiltonian to get a Brillouin zone. You don't. Okay, and that will come back later. Now, what is true is that we do care about the Hamiltonian because it wouldn't be useful if your Hamiltonian doesn't commute, right? If your Hamiltonian commutes, then it can act on each sector. Okay, it diagonalizes in this form. Okay, so that's why we do care that your Hamiltonian commutes. And so, so here I come to what I think it's common physical order. So first of all, I have to say that I've looked many times if somebody discusses, because what I'm going to say now is very simple, and I'm surprised that nobody else had said it before. So, so I apologize, and if anybody knows somebody already discussing these things, please let me know. But something that you will see, for example, I saw a talk by Sheinbaum when he was saying, okay, for non-interacting systems, we have a torus, we have the Brillouin zone, and we can use the topology of the torus. For interacting systems, that is lost. You don't have that anymore. And so we have to do something completely different, and that's when he came up with things like topological order. Okay? But is that true? Okay, so what happens when we have n interacting particles? Okay, so now I have a many-body wave function, and it depends on the coordinate of each of the n particles, and it lives in this Hilbert space, which is just the tensor product of the single particle Hilbert spaces, right? This is another way of writing it. And okay, so let me now suppose that my Hamiltonian is of this form. It's just what you would expect of having ions and having Coulomb interaction, right? If I translate just one of the xi's, then this Coulomb interaction changes, okay? And this is no longer a symmetry. So this will not commute with translation in just one coordinate. Fine? Okay? But it does commute with translations in all of the coordinates. Okay, so I can represent, so my many particle Hilbert space is also a representation of my group Z to the D. I just have to translate, so the action or the representation has to be translated in all of the coordinates. Okay, so as such, because this is a representation, it can again be decomposed over the Brillouin zone, and this torus is again exactly the same. Now, the physical representation might be different. This thing might no longer be momentum space. Yes?
Confused because usually you would anyway kind of ignore the center of mass motion, right? So if you translate all coordinates, you're basically translating the center of mass of this n particle.
Yes.
And that's not what we want to study anyway for this many-body system.
Well, I disagree, because precisely this momentum and these wave functions will give you topological invariance. And in fact, you can show that, for example, single particle invariants are stable when you include interactions if viewed in this way, right? But I wasn't going to discuss an example, but I recommend if you go to our paper, you can show, for example, that if you have a single particle system that has a non-trivial Chern number, then you can show that the many-body wave function has a non-trivial Chern number. Okay? So, fine. So now what happens? Well, like I said, this Hamiltonian is invariant under translations, right? If I translate all the coordinates, then I can write it this way. And again, my Hamiltonian decomposes so it diagonalizes again, but now this is the many-body Hamiltonian. And so we can look at the ground state of this Hamiltonian for each k, and I'm gonna denote this by sigma k. Are there any questions? Okay. So let me assume that the dimension is finite dimensional and it's fixed, and that Hn has a gap. Okay. Then if I consider for each Hamiltonian just their ground state space, I get a map. So this is collapsing a lot of information and ignoring higher energy and just looking at the ground state of your n-body Hamiltonian, and this becomes a map from the Brillouin zone to the subset of n-dimensional spaces in your n-body Hilbert space. Okay, and this thing here is what is known as a Grassmannian. You've used it a lot in the single particle case. And here I've used the, so you could ask, well, didn't the H depend on K before, right? What was it? Over here? Yes, okay. So why is it not depending here on K? Well, it turns out, so modulo things that Bernardo talked about, which is what happens when you have twistings that I will not discuss here. You can use that any Hilbert bundle is actually trivial. So you can rewrite this thing, which looks in principle complicated, as just a product of the same Hilbert space times your Brillouin sum.
There the compact open topology is a natural one.
Sorry?
There the compact open topology is a natural one.
You mean for Kuiper stream? Actually, there's a discussion that that I found, which is very interesting. So you're talking that Atilla and Segal, when they discuss twisted K theory, they worry about using compact open topology, right? And there's a discussion that I forgot the name of the author, but he talks about the fact that it's not really relevant that you could use the normal topology. You didn't the norm topology.
Yeah, you can use the norm topology, but you cannot use the colimit topology.
Yeah, I think part of the point is that, for example, the twistings that we use come from finite groups, and so the point is that the issue with Lie groups and having that doesn't appear in condensed matter, I think. Yes.
When you say this, you mean as like Hilbert space, not as vector bundles or the base space.
Right. So this will be a vector bundle. You're right. But what I'm saying is that here, to view this as a vector bundle, I had to use the fact that I'm looking at maps that go into a space that has n-dimensional subspace of a fixed Hilbert space, right? Here, the Hilbert space in principle varies with K. So you could imagine that somehow I'm getting something different as I vary K. But it turns out you don't, because there's a theorem that tells you that every Hilbert bundle is trivial in the norm topology. Okay. Huh?
From Dixmere
Dixmere duality. Okay. So okay, so this is bosons versus fermions, and so you can ask, okay, so I did it for n particles. What about if my particles are bosons or they are fermions? Well, it turns out that they're also representations of set to the d. And if you could think about it, what are bosonic or fermionic wave functions? Well, they're just sums, right, of products of wave functions. So I can translate all the coordinates, and I'm going to translate in the sum. So it'll be exactly the case, which at first glance it should worry you, because this is telling you that what you get is the same Grassmannian, whether it's bosons or fermions, right? It seems that topologically you're not getting anything distinct, and that should be worrying you a bit. Okay, but it turns out that there is a distinction, and that's because of the fermion parity operator, right? So for many body ground states, they had to, for fermions, they had to satisfy being an eigenstate of this fermionic parity operator, and it in fact becomes more relevant when I discuss crystalline symmetries, but I'm gonna skip it for now. So this is the main result of our paper that we published in JHEP, right? So if you consider adiabatic evolution, which is again varying a parameter slowly, and you have a gap, this will be equivalent to looking at homotopy class of maps. So this is an interpretation. Analysts always say, okay, you can do, if you want to do this rigorously, you can get more fancier things. I think Ogata and Sven Bachmann have something which they call C1 phases. But this is an assumption that almost everybody in the interacting and non-interacting literature do. They treat this varying a parameter as homotopy class of maps. And so what you would get for bosons is that these phases are equivalent to n-dimensional vector bundles, right? When your ground state is n-degenerate, you get n-dimensional vector bundles over this Brillouin zone. And for fermions, you get something very similar, but it has to respect this parity symmetry. So let me write it this way, which means that it has a symmetry action. Okay,
And the symmetry on the left is the time reversal symmetry.
Sorry?
The symmetry on the left is the time reversal symmetry.
Not necessarily. So it also pops up if you look at reflections and rotations, I think. But it's true that when you write for fermions time reversal symmetry, it has to square to, I think,
But you
minus 1 to the
you don't have any group on the right.
Yeah, yes.
That's C2, exactly. So you don't have any other group for the spin orbit coupling.
No, I mean, I'm not discussing time reversal symmetry here.
So how does it go on the left?
Sorry?
How does it act in the tora?
It doesn't. It acts on the base, on the on the target.
So it's just the invariant part.
Yeah. In this case, yes. So okay. Sorry. So are there any questions about this? No. Okay. I'm gonna assume it's either trivial or well, maybe you think it's wrong. If you think it's wrong, please point out, like Jacob did. Okay. Anyhow, so I want to make another disclaimer and just yes, sure.
So generally you want capital N to go to infinity.
Yes.
How does
Yeah. Okay. Very good question. So you can't do this. You can't do. So yeah, I chose the most. You're absolutely right. So I chose the simplest presentation of this thing, right? But there are two different ways of doing it. One that is in our paper is sort of like a midway, and it's just like taking a limit and considering Fock space. The other thing you can do if you want to be even more rigorous is to do the GNS representation. And if you do a GNS representation, right, you still have that set to the D. So if your ground state is translation invariant, your GNS Hilbert space will also be a representation of set to the D, and it admits again an isotypic decomposition, and you can do exactly the same thing.
For the CAR algebra, so what algebra are you doing GNS representation of?
Yeah, I mean, if you do fermions, I guess it's CAR, and then CCR if you do bosons, right?
So, like, what Fried and Moore did
Uh-huh.
is very, very similar. They just took the Grothendieck group of this
Yeah.
this monoid.
Yes. So that's a good point. So what we're saying here, so this is why the disclaimer appears here, right? So it's not exactly the same. There are differences because they get they get Grothendieck, right? They get K theory in general, and we don't get K theory in general. We have something that is, it depends on the dimension of your ground state space, the vector bundle that you get. And there are differences. It's not the same. There are characteristic classes, and there are things that don't survive in K theory, for example. Okay, so it's not exactly the same. But
well, they needed to impose some. They needed to, advocate for some equivalences to get the Grothendieck group, and this because they really want a Abelian group of phases.
Yeah, but in their case, what they're doing is they're adding trivial bands when they do this equivalence, right? They're adding trivial bands. So that doesn't alter the physics too much. It does when you consider fragile phases, and those will pop up next. But here, this is something very different, right? If you change the dimension of your vector space, you're changing your ground state degeneracy. So that's doing something very non-trivial to your system. Okay. So if I try to stabilize this thing, I'm talking about a system that has infinite dimensional degeneracy or something like that, or arbitrarily high degeneracy, and that's not the same. So it is very important for me to say that I'm not claiming that these are all the invariants that you can compute for many body systems. That would be ridiculous. I'm not saying that at all. What I'm saying is you can use some things that you would use in single particle topology that sort of survive into many body systems. And that's something that you already knew sort of happened. For example, the Chern number, the integer quantum Hall effect, right? That is very stable under adding interactions when you have the integer value, right? I mean, I'm not completely expert on that, but I think you have to do something very radical to change your system into a fractional number, and you would have to do a transition, right? So we already knew, for example, that. And okay, are there any more questions? Yes.
So earlier in another slide you had that for fermions it would be vector
Yes.
How can you explain that? Because usually we think that it's the fermions that are generally classified by vector bundles or the detos, and you found that for bosons. So
Yes, that's a good question. So
and also what kind of different classes would there be for these fermionic vector bundles?
yeah, okay. So I'll get to that in a second a bit more. But you're right that okay. Let me think this for a moment. So okay, so I think that this symmetry here is already implicit when you do the single particle picture, right? So when you do a single particle picture, you never discuss this extra symmetry of being a fermion, and somehow you write for bosons, I'm sort of getting things that look like the single particle picture of fermions, and then the many body thing for fermions, I'm getting something extra here. So you're right, but so we can discuss it a bit more later if you want, but I think yeah, for now the best I can come up with is that this symmetry sort of assumed the moment you go to the single particle picture. Yeah. Okay. So how much time do I have left? About 15
12.
minutes.
30.
Yeah. Okay. How am I doing on time? Okay, I think I can do this quickly. Okay, so now let's compare two SPTs, right? So suppose that my ground state degeneracy is equal to 1. So then it turns out that the Grassmannian is equal to what this is known as infinite dimensional complex projective space. And this space here turns out that maps into this classify the second cohomology of your Brillouin zone. So this tells us, for example, something that is also known. I think people at MIT had constructed a system when they have for interacting bosons, they have something that's like a Chern insulator. Okay, and this agrees with that.
Wait, so why is it HN? You have HN and dimensional Hilbert space, or how many dimensions?
Yeah, so for this case, n is the number of particles, which for now I'm keeping finite. You can do the infinite dimensional version, but it's much more complicated, so I didn't get into it. So n is the dimension of the ground state. N is the number of particles. Okay, so here I've been treating this as very large n, but finite, and then the ground state in this case I'm setting it equal to 1.
Okay. So H tilde is the infinite dimensional separable Hilbert space.
So H tilde would be an infinite dimensional Hilbert space, though it's not the same. It's not your original Hilbert space. It's a different one. It comes out when you do it's the same thing that comes out when you do a block decomposition, right? When you write this things over here, this space over here, it's not the same Hilbert space. Okay, it's a different one. It's usually L2 functions over your unit cell times would be what is left by the quotient. So it's something like, not exactly, but I think Jacob can correct me on this, but it would be something like L2 on RDN mod set to the D times TB. I think if you, yeah, okay. Okay, so sorry about that. So let me go quickly again. So okay, so you get this second cohomology, right? And it's not that interesting in this case.
It's a set. It's not a group, right? Like you have equivalence of
yes, yes, that'll be important. So here I'm using this thing as a set, but I'm using that you can distinguish each individually by the invariant, right? But I'm not using the group structure, and that will be relevant in a bit. So what about adding crystalline symmetries? Okay, so mathematically, so this is for two-dimensional, what are called wallpaper groups, and they were already discovered in the Alhambra. And mathematically, you write it this way. Let us not worry about that. The important point is that there's a P group, and this P group acts on the torus, right? So here's a technical point that I'm only going to discuss symmetric crystalline groups, because if you consider what are known as non-symmetric, and they're of this form, right? This is the point group, and it's there's a non-trivial action on sexuality. And I'm considering only these because it gets more complicated if you don't. Then you have things which are called twists, and I'm not gonna get into that. We haven't done it actually. So if anybody's interested in generalizing this to non-symmetric groups, please let me know. And so you have something which is, sorry, I forgot to put a P here. But you have, again, maps, but they have to be equivariant maps with respect to the P action on your torus. So, and what you get will be just the second cohomology group of your Brillouin zone, okay? And for fermions, this can be much more complicated, because it turns out that rotations and reflections can interact non-trivially with fermion parity. And so you have to do an extension of your point group, and what you get is just that. Okay, and so here we compare with the work of Thorngren and Els. And so as you can see, we get, for these different groups, we get some which are much bigger, some which are equal, and some which are smaller, right, in rank. And they are, however, they are very similar in many aspects. Like some of them just have the similar factors, right? And some of them just like miss one factor, things like that. Okay, so what does this mean? Does it mean that the work of Thorngren and Els is wrong? And I would claim that no, not at all. There are several possible reasons why they wouldn't match, right? So again, SPT systems assume something that is like short range entanglement, that what you mentioned, that you have stacking, right? That you have a group structure, and they also use TQFTs with this symmetry to and this crystalline equivalence principle. So short range entanglement means that we didn't impose anything about entanglement at all. In fact, about interactions. So interactions, as long as they're translation symmetric in this way, can be, as long as they depend on R, they can be something like Leonard-Jones potential or whatever. Your Hamiltonian will commute. So we didn't say anything, and two SPT phases could merge in our classification, right? So we would destroy an SPT phase and turn it into a single one using R. On the other hand, right, stacking is something that destroys some phases. It destroys what are known as fragile phases. Those are phases that can be described, for example, by bands that if you include a trivial band, they disappear. And so in principle, we could be considering fragile phases that are robust to including interactions as long as you don't close the gap. And those are trivialized by the SPT classification. And finally, the one which I think it's less likely, but I think it's worth discussing is, well, like we said, there might be difference between gap phases and TQFTs. So it might be that this crystalline principle is not always true. Okay, but that is very general, and I do think we should discuss it, but I think it's less likely. I think it's more likely that some of these things could be very relevant for what's happening here. Okay, and you could then say, okay, you haven't showed a single example. You haven't given me a Hamiltonian and showed that it's in one of these non-trivial phases, right? And I have two examples that I'm not gonna show because I think they're not very illuminating. But in general, this is like one big criticism you could make of what we're doing is that, okay, we know how to compute them, right? For how to compute the groups and how to classify them. But this theorem is more like the fundamental theorem of algebra, right? It tells you that given a crystalline symmetry, you have this amount of phases and that they exist. But it doesn't tell you almost anything about how to construct a Hamiltonian that represents one of these spaces. Nevertheless, unlike the root formula that doesn't exist for degree 5 and higher, these things do exist. It's just that mathematically they're not that easy to construct, at least in the mathematical literature. Maybe Bernardo or Kiko know something about it, but these are very complicated things to construct in general. But also this is very important, like single particle systems, right? Systems with a single band, but that they have this crystalline symmetry. They could represent some of these spaces, right? If they have, so if they land in our classification, then they should be robust to adding interaction. So in fact, you can use a lot of single particle systems to construct this many body invariants. And if you show me some single particle system, then I should say, okay, then we should try adding interactions which are translation invariant, and we should see that this invariant remains the same. Okay, so if you know how to do that for single particle cases, please let me know. And okay, yeah, we still have a bit of time. So remember that I was complaining about Kitaev's conjecture, particularly for free fermions, right? That this thing didn't look at all like it depended, like the degree didn't depend at all on the dimension. So what is going on? So there's this deep result that is called T-duality that was first discovered in string theory, but then it moved on to condensed matter, and it's been applied by some people in condensed matter, particularly Guo Chuan Tiang. I recommend reading a lot of his papers. And so he explains, I mean, he didn't discover this, but he has applied it in condensed matter, and so he has some notes, and you can read there or in his papers that there's this isomorphism between K groups. Now, this is very important because this torus here is the real space torus, and here, for example, you have KR theory, and computing KR theory, you get something complicated because this has fixed points, right? So you have to take into account the fixed points. But sorry, was there a comment? No. Okay, but here you have what is known as KO theory, and this has no fixed points at all. But the only thing you did was raise the degree, and you raise it precisely by b, right? The same is true for quaternionic K theory, which is the one that appears when time reversals first to -1, and it's true even in the complex case. Okay, so this is a very non-trivial result. I'm not gonna discuss the proof here. So that means, okay, that we can replace the groups that were appearing here by groups that depend on the dimension, but instead of being evaluated at the momentum Brillouin zone, they're evaluated at the unit cell torus. Okay, at the real space torus. Okay, and this fits with Kitaev's conjecture, right? If you look at it in real space, then it's true that the loop space of this thing, so his conjecture is true. This is just a statement of this conjecture. But this relied on a very heavy result for the free fermion case. Okay, so however, this has changed my mind very recently on the conjecture. One thing to check was if it was true in the free fermion case. We see that it is once you use this big result, and so this gives me hope that that the conjecture will actually be realized. Okay, and well, remember that I said remember this number d plus 2, right? So remember that the shift in degree here is by b, and here, what did we get? Well, we got H2, but of the Brillouin zone. And what do they have? Well, it turns out that the group that they have is equivalent to this group with B plus 2 in the real torus. So we have exactly the same shift as T-duality. Okay. However, T-duality is not an equality in cohomology. Here it fails. Okay. So there might be some reason related to T-duality. So how the failure of T-duality in cohomology to explain why we are getting different results. But to me, it's very interesting that we had exactly the same shift. Okay, and I think I have about 2 minutes. Okay, so I'm just gonna mention you can add what about adding Atlan's invariant symmetries? Okay, and so these have sort of already been classified by the work of Gomi and Benitez for d less than 4. And so we could use that to also construct topological invariants for many body systems, and again using single particle invariants, right? Systems with 2 bands in this case. And what about the real torus, right? What I presented was a version that sort of generalized the Brillouin sum to interact in systems. Can we generalize and use the real torus instead? Yes, we can. So will this help understand a partial result for T-duality? And it may also help in computing groups because there's no more, you don't have to worry about the action of k going to minus k, say, in time reversal symmetry and things like that. Okay, and this was the last thing I want to talk about, but I don't have time. It's what happens when you have a boundary and results by Corey and Ogata also, and sort of there's a way of trying to use this and trying to generalize the work by Emile Prodan and Schultz-Watlez and several other people of how to describe the conductance as a pairing, as an index pairing in K homology and K theory. And there's a version of that using von Neumann algebras. And so, yeah, I was hoping that maybe this can be generalized. And the point is that to do this, you need a space to do it, right? And the space would be, again, the surface, well, in this case would be the surface Brillouin zone, right? If you add a surface, you lose a direction of translation, but you still have translations in the direction parallel to the boundary. And so that would be your space, but you would have to do things with von Neumann algebras. Okay, so let me end here. Thank you.